Hello. The United States faces a number of challenges, including urban population growth and tremendous per capita resource consumption, peak oil and the global energy transition, and climate change. Although these problems are addressed in the research literature, the lack of a robust, contiguous regional spatial planning instrument in the United States means that regional climate change mitigation or adaptation strategies are not widely applied. The driving research question in this study is, how can the USA supply the basic resources and energy demands of a growing urban population in the context of climate change, the energy transition, and competing global demand for basic resources? Based on modeling from Rubel and Kotek in 2010, figures 1 and 2, the redistribution of Köppen climate zones will have 4 basic effects, including 1, the northward expansion of the warm CFA zone will replace the snowy DFA and DFB climates in the upper Midwest and Northeast. 2, northward expansion of the tropical AM and AW climates into the central Florida peninsula. 3, northward expansion of the dry BSH and BWH steppe climates into the Midwest and upper Midwest and Rocky Mountains. And finally, the warm dry summer climates, CSA and CSB, will expand from the Pacific coast eastwards into the high desert interior and the northern Rockies, replacing snowy climates at higher altitudes. The literature review, figure 3, focused on effects of climates and ecoregions on carrying capacity, integration of human and natural systems, methods to quantify and manage material flows and the urban metabolism, and environmental footprint methods, including the water, carbon, and ecological footprint. Although current environmental footprint methods are promising, they addressed only a limited number of components or returned land units that make assessment of material, water, or energy flows difficult. To fill this gap, the work sought to develop a regional, unit-specific, spatially explicit environmental footprint approach for the United States. This led to the development of the County Diagnostic. As concept framework, the County Diagnostic expands on the Dissipative Ecological Unit, or DEU, shown in figure 4. That describes the fundamental cycling of material, energy, and water in natural systems with a very low percentage of entropy. The County Diagnostic builds in components needed to support the human urban metabolism to the DEU under one of the 4 principal categories of producer, consumer, detritus, or decomposer, shown in figure 5. This approach leads to an integrated environmental footprint assessment that expands on the existing footprint family and includes solid waste, food waste and sludge, wastewater, renewable electricity potential, and existing electricity potential, as well as an area for ecosystem conservation, figure 6. For all components, both a resource capacity and resource demand is calculated to enable a unit-specific accounting and to assess material, water, or energy balance. For regional planning, the county is an excellent unit because a wide range of unit-specific spatial data exists at the county level, and counties can be aggregated to assess large areas such as river basins, councils of government, or large regions affected by climate changes. The County Diagnostic approach could help fill the gap of regional spatial planning in the United States. By far, the largest effort of this study focused on the methodological development. The method, shown in the center column, summarizes flows into 6 categories of food, water, zone of conservation, carbon, electricity, and organic and municipal solid waste. Given the complexity of the calculation method, the most efficient formulation of the method was to use mathematical formulas where variables represent explicitly defined datasets and timeframes. Countywide demand and capacity are calculated for 19 factors within the 6 categories using equations specifically developed for datasets available at the county scale for the entire USA. In total, the method encompasses 31 capacity equations, 19 demand equations, and 87 data sources, including spatial, tabular, and remotely sensed data, as well as conversion and calculation tables from peer-reviewed scientific literature. Given that each of the 6 categories has a different unit, tons, megawatt hours, cubic meters, then a normalized difference index, or NDI, is used to compare capacity and demand, resulting in a value between +1 and -1 for each of the 19 NDI values. The NDI is then plotted as a vertical waveform diagram so that a simple graphical output relays the results of the model for a county in a way that experts, elected officials, and laymen can understand. The vertical waveform diagram is shown on figure 19. To illustrate the entire process, I walk through the demand and capacity calculations for just one formula, cereal grains for human consumption. Left of figure 8, in the upper center column of the poster, the total capacity of cereal grains in tons, F3C, is calculated from the USDA's National Agricultural Statistics Service, or NAS, as the total tons of cereal crop products P, defined for human consumption, which is table 4.2 for cereals, per county X and per year T. This product is added to the total tons of legume products P, defined for human consumption per county X and per year T, to arrive at a total capacity of cereal and legume crop capacity. Demand for cereal crops follows the USDA MyPlate daily dietary recommendation in a bottom-up per capita approach, where the total number of ounces per day of cereals is multiplied by 365 days and converted to tons, then multiplied by the total population of a county. Since MyPlate does not distinguish between cereals and legumes, and the dietary properties of cereals and legumes often overlap in their carbohydrate content, then cereal and legume crop products were combined simply under one category, cereals. The total tons of capacity, F3C, and demand, F3D, are fed into the NDI formula, which is identical to the normalized difference vegetation index and returns a number between +1 and -1, where 0 is equivalent to balanced capacity and demand, positive values indicate surplus, and negative numbers indicate shortfalls. Here in figure 9 for Schoharie County, you can see that the demand for fruit and tree nuts, hay or grass, and feed grains for livestock exceeds capacity, whereas capacity for vegetables, cereals, protein, and dairy is sufficient for the population demand. To understand the performance of the county diagnostic method and how county-wide balance is affected by ecoregions, the county diagnostic is compared in a 6-county case study, with each county from a different level 2 ecoregion within the Eastern Temperate Forest. The vertical waveform diagram for each county is overlaid in figure 19, where you can see that each county performed a bit differently, and no counties were positive in all categories. The 2 counties nearest to each other, Schoharie and Garrett in purple and red lines, have a similar vertical waveform diagram. To better understand the driving factors behind the NDI distribution and their similarities or differences, a categorical principal component analysis was applied, which is shown in figure 20. The CAT-PCA analysis, figure 21, results in 4 dimensions that were interpreted based on the correlation of the NDI factors. The factor explaining the greatest variance is simply human and livestock population that drives demand, followed by water availability as a limiting factor, then affluence and the application of technology, and finally, the area devoted to ecosystem services. An alteration in any one of these 4 components will result in a change of balance in many of the model factors. The conclusion regarding metabolism of counties is that they are non-equilibrium thermodynamic systems. That is, they're open systems. They rely on material, water, gas, and energy exchange to support the human population. In almost all counties, the application of nutrient, organic, and material solid waste recycling technology, as well as renewable energy, is far less than what could be applied. These represent areas for increases in efficiency, and thereby could be considered climate change mitigation strategies that reduce overall material and energy consumption, which lead to GHG emission reductions and thus reduce climate change drivers. Regarding climate changes in the Eastern Temperate Forest and the 6-county case study area, the areas affected by climate changes based on the SRES A1F1 scenario through 2100 are depicted in figure 18. The Eastern Temperate Forest will be affected by an expansion of the CFA climate type in higher latitude areas, replacing the snowy D climate types, and in high altitude areas of the Appalachian Mountains, replacing the CFB climate type. Snowfall reductions could affect annual meltwater cycles and thereby reduce summer stream flow. In Florida, the AM and AW climates, both with a hot summer dry season, will move northward into the Florida Peninsula, probably exacerbating water capacity during the dry season. This could affect water summer availability in Tampa. The expansion of the warmer climates northward could be a food and solar energy production benefit for many areas of the upper Midwest or Northeast, increasing mean temperatures and shortwave radiation with longer summers. However, longer and warmer summers also increase evaporative losses, and thus the need for irrigation. In Schoharie County, the total water abstraction already consumes 73% of available stream flow. Thus, crop expansion would hit water as a limiting factor. Dimension number 2. Thank you very much for visiting this poster. If you're interested in this research, the method and the entire book is available via Springer Nature for small fee, or as an electronic download from the TU Dortmund Eldorado system. Both references are included in the poster below. Have a great day.